we found well, I mentioned a nice formula for the permutohedron, so for the associahedron, which turns out to be given by a sum of simplices. The sum of, well, I guess faces of a simplex, which are also simplices, delta sub I comma j. That turns out to be a realization of the associahedron. Here, delta I is the convex hull of EI, where I is an I. All right, and yeah, and the example here is that if you take a triangle plus a line segment like this plus a line segment like this, what you're gonna get is gonna look like a pentagon, this shape. And in general, in higher dimensions, it's going to have Catalan many vertices. And so today I'm going to try to prove this, and I'm going to try to do this more generally. Question? A formal definition for which side? It's the Minkowski sum. So you just you take each point, you take a point from each of the summons, and then you sum them up, so you get all possible collections. Yeah. All right. So today, what I'm going to discuss is graph associahedra. The graph associahedron is a generalization of the associahedron for an arbitrary graph. Suppose let G be a graph. I guess by that I mean a simple graph. There is no multiple edges, no self loops, nothing like this. And I'm gonna assume that the vertices of G are the set of vertices is just bracket n. So the vertices are labeled from 1 up to n for simplicity. And then what I'm gonna define a I'm going to define the analog for an arbitrary graph of all such intervals. So and it's called a graphical built-in set. Graphical built-in set is just by definition B sub G is the set of all, well, it's basically the set of all connected induced subgraphs of my graph. Set of all subsets I such that the restriction of the edges of G to I, well, the induced subgraph on vertex set I is connected. Later, I'm just going to say that I is connected, and by that I mean that you have your graph G looks like this, and then you can choose any collection of vertices, but they have to be connected by some. Well, there could be cycles, but and for example, if G is a path, 1, 2, up to n, then built-in set of G is the set of all intervals from I up to I to J, I and J are between 1 and n, I is less than J. Okay, so in this sense, this is when G is a path, the corresponding graph associahedron should be the usual associahedron. Any questions so far? And the definition is that the graph associahedron is the Minkowski sum for I over all. So it's the sum over all connected subgraphs of G of the corresponding faces of the simplex. So that's not the original definition, but that's sort of the actual polytopes were constructed earlier than this definition was obtained. But anyway, this could be a definition. So you get some, I mean, you clearly get some polytope, and so question is, what are the faces of the associahedron, of the graph associahedron? Somehow these should correspond to like generalization of triangulations, right, for arbitrary graph. So so let me know, I mean, unless anybody has a guess for what the faces should be, I guess. Yeah, it's kind of tricky, right? You have this Minkowski sum. We know how to find faces of the Minkowski sum, but still it looks kind of tricky, right? But so let me actually write it down. A definition which is due to Carr and Devados. So this definition is Plasnikov 2009, which was 3 years after these guys were the ones who constructed the polytope originally. Okay, so the definition is that a G tubing, or simply a tubing, is a subset of the built-in set. So I'm going to denote it by fancy T. It's the subset of the built-in set. And I don't want to take, so notice that here I'm allowing the whole graph to be in my set, and any singleton, and also the empty set. So, but for a tubing, I don't want to allow the whole graph or the empty set to be part of my tubing. Then a tubing is a subset like this, such that the following two conditions are satisfied. First of all, for any two sets in my tubing, so each of them is a connected subgraph, and the claim is that any two sets should be either nested or disjoint. So any two sets are either nested, and nested means one is contained inside the other, or J subset I, or disjoint. That's one condition, and the other condition is very simple: no adjacent tubes. What is an adjacent tube? Well, two tubes are adjacent if I and J are adjacent if they're disjoint. Intersection is empty, but their union is a tube. Their union is connected. But I union J is connected. Okay, so very simple. These two conditions, and so that's the notion of a G tubing. So let me maybe try to draw an example of a G tubing. I was going to try draw a very random graph. 1, 2, 3, 4, 5, 6, 7. Here's the graph. And then, oh, maybe somebody can tell. Somebody tell me a tubing one by one. Just give me a connected set and then some other one so that they form a tubing, and just keep going until we're stuck. 1, 5, 4, 7. Okay. Nice. This is connected, so this is good. Anything that's compatible with this? 1, 5, 4, 7. Okay, this is going to be tricky to draw. All right. Okay, 1, 5, 4, 7, and 1, 5, 4, 7, 6. Okay. Yeah. 5. You want to take 5. Or 1, 5. Okay. 1, 5. All right. Everything except 2. All right. 1, 3, 4, 5, 6. And just 7. All right. Does that work? All right. Anything else? Just 1. Okay, interesting. Just 1. Anything else? Seems like no. Yeah, you can't take 3 is going to be adjacent. Yeah, all right. So how many do we get? 1, 2, 3, 4, 5, 6. 6, 7. All right. And so this is supposed to be a vertex of the graph associahedra. I mean, seriously, it's a, yeah, so let me state the result. So the claim is that theorem, which so Carr and Devadas 06 and Postnikov 09 is that the phase lattice of the graph associahedron with that definition is the coset of the tubings ordered by inclusion, or ordered by reverse inclusion. In particular, this is a G tubing. It's maximal by inclusion. So it corresponds to a vertex of my graph associahedron. And so here, so these guys just show that there exists a polytope. There exists a polytope whose phase lattice is the poset of tubings. And then Postnikov actually gave this realization with the simplices. All right, so okay, let me try an example for the usual associahedron. Maybe G is the graph 1, 2, 3, 4. Let's do 1, 2, 3. Then 1, 2, 3. I'm supposed to get a pentagon. Can somebody give me a maximal G tubing? One, 1, 2. Oh, 1, 2, 3 is not. Yeah, I'm not taking the whole set, but I could. But it's just you can trivially add the whole set to each. So it's going to be like a product of. Yeah. Anyway, so what's the next one? 1, 1, 3. Oh, hold on. 1, 3 is not connected. Three to 3. So I want it to be connected to this one. I want them to share a single tube. Just one. Well, just. Oh, 1 and 3. Oh, nice. All right. Okay. Yeah. So there is an edge here, which this edge corresponds to just the tubing 1. Okay. What's the next one? 3 to 3. What's the next one? 2 to 3. 2 to 1. Nice. So we do get a pentagon. That's pretty cool. Well, right. So these are all the vertices. So these in the Hasse diagram, this would be the minimal elements of the. Yeah. So the Hasse diagram of face lattice of the associahedron would have all these 5 things. Yeah. 1, 2, and then 1 and 3, etc. So these are the minimal elements which cover the empty face, and then there's these 2 are covered by this tubing, and etc. And here on top, I just have the empty tubing. All right. Yeah, so it's pretty cool that such a simple notion of tubings gives me a polytope. It's kind of unexpected. And yeah, let me try to prove the theorem. Yeah. Oh, so why do we have no adjacent tubes? Yeah, that sounds like a weird condition. And what can I say? I mean, without this condition, I guess it doesn't work. You don't get a polytope. I mean, it's really a kind of a creative task to find a definition which would give you a polytope. But there is some history to this. This comes out of some wonderful compactifications of hyperplane arrangements and things like that. So this condition actually comes out. There is a more general setup where somehow this is, I guess, more natural. But yeah, I agree that for graphs, you would want to remove this condition. And later, we're actually going to see an example where there is no condition like that, and you still get a polytope. Any other questions? All right. So yeah, I guess I'm going to erase the notion of a G-tubing. Let me try to prove. Well, okay, so what do? We have the definition. The associahedron is the Minkowski sum over all connected subsets of the corresponding simplices. How do I find, let's say, a vertex of this polytope? Has to be one of the EIs. Okay, well, that's for each, yeah, but that's a good idea. So for each individual summoned, has to be one of the EIs, right? But how do I choose? Yeah, what's the general algorithm for if I give you a Minkowski sum, what do you do to find the vertex? Okay, you want to take let's say you take a generic vector. Fix a generic vector h, h1, hn. All right. Then, of course, the corresponding face of the associahedron is the sum of the corresponding faces of the deltas. And each of them, right, so this is a conic cell of a bunch of basis vectors. So the vertex is going to be the one maximizing the value of h, hi, which is maximal. So f sub h delta I is ei is the maximum. Yeah. Now, how do I want to go from here to a G-tubing. How do I connect this to the G-tubing? And so the procedure is actually going to be tricky. What I'm going to do first is I'm going to find the global maximum of my vector h. So let's say I is the maximum. It maximizes hi. Then what I'm going to do is I'm going to construct a certain a rooted tree. So which I'm going to denote by T sub h. So how does this tree look like? T sub h. It's going to have root labeled I. So if you imagine your graph, your 1, 2, 3, I, etc. So if I is where h takes its maximum, then I'm going to designate I to be the root. And so which information do we get from knowing that hi is the maximum coordinate? If you look at this sum, whenever your connected component contains, well, whenever your connected graph contains I, then I has to be the vertex. So basically, f sub h of delta capital I is e lowercase I whenever capital I contains little I. And so in particular, I only need to consider connected components, connected subgraphs which don't contain I. So that means I can remove I from my graph. So I is the root of my tree, and then what I'm going to do is I'm going to remove I from G, and then proceed recursively for each connected component of G without I. So in other words, if I remove I and then G without I splits into several connected components, then I can just solve my problem on each of those connected components. Yeah? Well, not quite the breadth. Yeah, not quite the breadth first search, but I'm just saying that once I know that I is maximal, I know the result for all i's which contain, for all capital I's which contain a little I. So I can consider only connected components, only connected subgraphs which are connected inside this graph here. So, and the problem is sort of recursive, right? So if your G looks like this, I know I is maximal, then I remove it, and then I get two connected components. So I need to pick a maximum here and a maximum here, which are both of them are going to be less than I, but I don't really care how they compare against each other. So I guess next step is that for each connected component of G minus I, choose the maximum, choose J that maximizes H sub J along that connecting component and make it a child of I in C sub H. So I know this is a very bad explanation of what's going on, but maybe I should try an example. Maybe let's say G looks like this. 1, 2, 3, 4, 5, 6, 7. Okay, so maybe somebody can tell me which of, let's say I choose some H. So which of these vertices, just choose one which has the maximum value of H. 3. Okay, so I is 3, in which case, so my tree TH has a 3 as a root. Okay, so I remove 3 from my graph, and so I get 2 connected components. Now, somebody tell me a maximum h inside of each connected component. 1 and 6. Okay, then I remove 1 and I remove 6. So here I have only 2. And here I have 2 subtrees, 4, 5, and 7. Which is bigger, 4 or 5? So I get a tree. From any ordering of my original vertex, I get a tree like that. And then the claim is that such trees are in bijection with G tubings. And so to get from a tree to a G tubing, what I do is I look at each vertex and I take all of its descendants, except for the root. For each other vertex, like here for 1, its descendants are going to be 1 and 2, and that's going to be one of my tubes for each non-root vertex J. Take, add the set of its descendants to the tubing. For example, let me try to recover my graph. 6, 3, and there is a 1. So what's going to be the tubing in this case? Just 5, just 2, and just 7. Yeah, these are the leaves, so they are 7, 5, and 2. Okay, what else? 1, 2. Oh, nice. Okay, so what else? 4, 5. 4, 5, 6, 7. All right. So this is a G tubing. And the claim is that the set of trees I get, basically any 2 H's give me the same tree, if and only if they give me the same vertex. And such the trees I get are going to be in bijection with tubings. You can add, no, but then, yeah, if you add, let's say, this part, then it's going to be adjacent. But if you add all except the 3, not connected. Yeah. It's actually non-trivial to see that it works. So exercise, finish this proof. All right, any questions? Yeah. Yeah, I guess it comes out of the hyperplane arrangement story, but I don't even remember how. There's some algebraic geometry going on. You do some blow-ups and stuff. Yeah, somehow being non-adjacent is important for blow-ups. Well, this is all really backwards, because so the notion of these wonderful hyperplane arrangement compactifications was obtained in '95 by De Concini and Processi. So '95 is the definition, and then the polytopes was constructed in some different way in 2006, and then the proof I'm given is from 2009. So it's all completely backwards. Any other questions? Yeah. Right. So yeah, of course, yeah, you're right. In general, after I have picked a generic H, I then have to tell you what happens if H is not generic. That you indeed get basically yeah, I mean, you still get a tubing, but yeah, anyway, so usually you do the proof for generic H, and then somehow you have to say that sort of the same argument works for arbitrary H, but of course it's an exercise as well. Right? Any other questions? Which, by the way, oh, what is the dimension? Hmm? It's n minus 1. Yeah, it looks like here it's supposed to be, the dimension is 2, and you have 3 vertices, so it should be n minus 1. And here we have 7 vertices, and then this tubing has 6 elements. Right? It corresponds to the vertex, so it seems to work. Yeah, but it's actually not quite trivial to prove. Right? But anyways, let me try to erase this. Yeah, so let me give you a few examples of graph associahedra. Because of course you have this general procedure, but it would be nice if for some nice graphs you would get nice polytopes. And one example is the one right here. So, if G is a path, then the associahedron G is the associahedron sub n. Well, yeah. This pentagon corresponds to n equals to 3. Yeah, so it's exactly the same. And it's a path on n vertices. And then another example, which is nice, is when G is a cycle. So if it's an n cycle, 1, 2, all the way up to n, then the corresponding associahedron is known as the cyclohedron. And was constructed in '94, coming out of some knot theory. But basically, so you can define it in terms of tubings, but there's another natural definition. So another name is it's the type B associahedron. So there is it's in some sense it corresponds to the root system of type B. And another interpretation of the vertices is that vertices correspond to centrally symmetric triangulations. Of A2 and gone. So I should give you an example. Let's say I take the hexagon, and then I want to try to draw the corresponding cyclohedron. So for the usual associahedron, you just get triangulations. For the type B associahedron, you get triangulations which are centrally symmetric. So there's always this one diagonal, which is like the diameter, and then the rest has to be centrally symmetric. No. So the vertices are centrally symmetric triangulations. The edges and higher dimensional faces are centrally symmetric subdivisions of I2 and on. So I can, let's say I erase this edge here corresponds to the hexagon where I erase this diagonal. No, the other way around. I keep this diagonal, but I erase the other stuff. All right. So there is one more example that I want to do. Well, actually, there's some other example which I'm not going to do, but I'd like to mention. So if G is a star like this, then you get some nice polytopes, which are called, you get a polytope called the stellahedron, which I'm not going to discuss today. But then finally, let me mention one more nice example. Let's say G is the complete graph. What's going to be the polytope? Permutahedron. Interesting. Why permutahedron? Oh, okay. So each tubing is going to be. Okay, all right. That's a nice idea. Now, indeed, the corresponding G associahedron is combinatorially equivalent to the permutahedron, because if you have a complete graph, and you try to choose a maximal tubing, then basically you can choose any vertex, and then any 2-element set, and then any 3-element set, and any 4-element set. So they kind of tubings, maximal tubings correspond to permutations. You can't really, once you have chosen a vertex, you can't really choose anything that does not contain a vertex, because then there are going to be adjacent tubes. So it's the permutahedron. And so what to me is surprising about this result is that we get yet another formula for the permutahedron. Permutahedron is the Minkowski sum over all non-empty subsets I of these simplices. So we have like now 3 formulas for the permutahedron as a Minkowski sum, and let me try an example. Okay, let's say take the triangle, right? So yeah, let's say n equals to 3. What are going to be my summands here? Okay, so the 3 points I can discard because they only shift my triangle, but indeed I take all other subsets. So the whole triangle plus the 3 sides. And what I get is, so I draw a triangle, and then I take one side, and then another side, and then the horizontal side. So I don't get quite a regular hexagon. It's important to understand. Still, I get something that's combinatorially equivalent to the. Pretty cool. Right. Yeah, the other ones are, yeah, they were affinely, yeah, I mean, if you choose the shift, they're just straight up equal to the hedron. This one is not. And also, by the way, I don't know how to generalize this to root systems. All right. So any questions so far? All right, so I'm going to ask a question, which is going to motivate, I think, the next lecture or so. Question is, we have, for every graph, we have an associahedron. Well, what about not graphs but posets? Do you get an associahedron for every poset? Or what kind of polytopes can you associate to a poset? That's the next theme. And one natural family of polytopes is the order polytope. So yeah, and later order polytopes are going to be important to us in several different ways. So I'd like to define them right now. And the definition is actually quite old. So that's Stanley 86. And so let's say you have an arbitrary poset which is bounded. Let P be a bounded poset. And bounded means that P contains a minimal element and a maximal element. And the minimal element is denoted 0 hat, maximal element is denoted 1 hat, and for any, they satisfy that any x is between them, any x in P. So let's say you have such a bounded poset, 1 hat, 0 hat. Then the order polytope is just by definition, it's a very simple thing. Order polytope is the set of all, basically is the set of all order preserving maps from P to the line segment. It's the set of all x's in, by R to the P, I'm going to denote the set of assignments of numbers to the vertices of my poset. And so the condition I want is that xi less than or equal to xj if I less than or equal to j in my poset, and x0 hat is 0, and x1 hat is 1. All right, so you just assign, you put 0 here and 1 here, and then you want the labeling to be weakly increasing along the poset. That's the definition. So for example, let's try a few examples. Let's say P looks like this. 0 hat, A, B, 1 hat. What is the order polytope? Simplex. Something like this, or something like this. A square, interesting. 1, 1. Yeah, indeed, if you look at these inequalities here, right, A has to be between 0 and 1, and then B has to be between 0 and 1. All right, and I can try another one, maybe something like this, 0. If it's a chain like this, then what do I get? A simplex. Is it going to be above or below the diagonal? A is less than B. Above. All right, cool. 1, 1. Yeah, so these order polytopes are pretty easy to deal with. And yeah, let's discuss the faces. What are the faces of the order polytope? Or maybe even the facets. What are the facets? Faces of the order polytope. Any ideas? Hmm?
This can be like all the three.
Okay, so you want one of these to be an equality and the rest to be inequalities, the rest to be strict inequalities. I see. So you glue, right? You have to. You want to glue two adjacent vertices, right? You can't glue B and 0 hat without, because that would force A to be also glued to them. So, yeah, so the facets are in bijection with the covering relations. In P. All right. And what about arbitrary faces? Glue one more. Well, I mean, arbitrary, if it's arbitrary dimension, then it seems like you glue an arbitrary set of edges, right? You take the Hasse diagram, and then you just choose an arbitrary set of edges and you glue them, so you get like a partition of your opposed set. So guess arbitrary, let's say contract an arbitrary set of edges of the Hasse diagram of P. Does everybody agree with this description? No. So what do you mean by strict contradiction? You mean something like this? I see. Okay, nice. All right, yeah, that's exactly. So this is. Yeah, so except for this, yeah, next time I'm going to give you a formal definition, but basically this example is forbidden, right? If 1 is equal to 3 and 2 is equal to 4, implies 1 is going to be equal to 4 and 2 is going to be equal to 3. So you have to include these edges together. Yeah, anyways, I'm out of time, so next time I'm going to continue from this point. Thanks, everybody.